So let's take suppose you're interested to obtain the probability of x will be greater than let's say 4. Okay, and under this the distribution of x following the normal distribution with parameter 0 comma 1 means it is a standard normal. Okay, so if you just observe here, what you can observe, the original distribution is normal, which is f of x, and now I'm interested to obtain the probability x will be greater than 4. So obviously you know that this is a basically your rare event, right? Because x is greater than 4 in the sense that obviously it is going to be a rare event, because hardly some value you will be getting greater than 4. The probability is very less. Am I right? Probability is very less in this scenario, correct? Just a second, I'll just record it scenarios, store it here on this slide. Yeah. So how one can get the probability of x when probability of x is greater than 4 in this scenario, or x will be less than -4, like that. So if you just observe, this is basically a certain integration. You will be get may or may not be some observation which is greater than 4, because hardly few values will be there after 4. Their probability become a very less. Okay, so suppose you want to generate, let me say 10,000 observations from that particular normal distributions. Okay, you're generating the from the norm, so R norm with this n comma 0 comma 1. Okay, means 0, standard deviation 1, and you are obtaining the probability which is length of length which is greater than 4. So x will be greater than 4, and since you are interested on probability part, so if you divide it by this n, this will give you the probability of x will be greater than 4. Okay, which may give one or two values only, because of it is certain because of it is the rare probability. Okay, hardly few values will be there. So we can get this probability value. So just look at this answer, 1 minus probability CDF of that R norm under 4 comma 0 comma 1. Just look at this. So this is your generating 10,000 observations from the normal. Just get the probability value. Look at this probability. So hardly it is coming. That means it is coming 0 itself. Means there is no observation generated from this x whose value is greater than 4. No observations we are getting. Right? Now look at the actual probability of this particular value. It is coming 3.16 in 10 raised to e raised to minus 10 raised to minus 5. So this probability is very less, very less, right? But this value is coming 0. But if you just run once again here, this value again it is coming 0. Now look at this, because in this scenario you have getting only one values, you're getting only one observation which is greater than 4. So 1 upon 10,000 will give you the probability of this value. Are you understanding what I'm trying to explain here, students? This is a very important concept. Let's look at the values. So again, one value. It may happen always 0. It may happen, but we are just getting only one observation which is greater than 4. But look at 0. Now here we're getting 3 values. Here we're getting 0. So many times you may observe we are getting the observation which is 0. Means no observations we are getting from that particular genetic observation. So in this scenario, our this Monte Carlo integration fails because sampling is not done properly in that scenario. So what we can do in this situation? So that's why this particular technique fails, and we are going to the important sampling concept. We are introducing the new sampling. This is called importance sampling. Okay, so I will just give you the brief idea how and why the important sampling is used and how it is used, and then because of this problem, because of here when you just observe here we're getting only 0 observations. It is not, means we are not getting exact probability here. Okay, so let us understand first what is the basic of your important sampling first, and then we will have the problem based on that. Okay, so let's take down this. So I'll just take the here. So look at this important sampling. What the first says. So usually the problem is to be estimate. What is the problem? The problem is to estimate the values of mu. Okay, so we have to compute the mean value, which is expected value of my h of x under the given probability or any function. Okay, where x follows that certain probability. Maybe it may be uniform, it may be Bernoulli, it may be normal and all. Okay, so one can very easy to compute this mu, which is simply your expected value of p h of x, which is same as integration of h of x. Okay, integration of your h of x, you can say p of x dx. Okay, or you can say f of x dx, no problem. So here what happened, the ordinary Monte Carlo method, what says, the ordinary Monte Carlo method, which is your OMC. First we draw a random sample. First we draw a random sample of size n from P, correct? We draw a random sample of a size P from that given period, and let it be, let's say x1, x2, xn. These are my sample values, and then based on these sample values we estimate mu hat, correct, which is 1 upon n summation I is running from 1 to n h of your xi values, right, which is the estimate of, which is an estimate of mu, correct? So this is your usual method which we have seen maybe in the first 2 examples. But here, if you just observe here, what is actually the Monte Carlo method, Monte Carlo method are the methods which solve deterministic problem using stochastic method, using stochastic methods, where simulation do exactly opposite job. They solve stochastic problem, they solve stochastic problem through deterministic procedure or method. So what I'm trying to conclude here, if you just look at this expression, this is basically your deterministic problem. It having only one and one solution. It's not like the one student will get one answer, other student will another answer. No, because it is integration. So it will always give me the, so this is my deterministic problem. Using this probabilistic, using this stochastic method, I'm getting the estimate value. I'm using the Monte Carlo method. Deterministic problem will be solved using the stochastic method, using the probability sampling. So here I'm generating from the probability first, using the probability P. These are the sample. So here actually I'm estimating that. Here actually I'm computing the estimate of the value. Getting the point? So here you have actual value, which is the integration of this value. This is a deterministic problem. But I am solving through the stochastic group. I am solving through the probability concepts. So this mu hat is your estimate of your mu. This mu hat is your estimate of mu. But what happened under the importance sampling? Under the importance sampling, we do exactly same. We solve the stochastic problem through the deterministic procedure. Now how it is see. So suppose you are generating the observations. Let's say just note this. Just note this part. Let's scroll down a little bit here. Note that the mu hat n is an unbiased estimator of mu, and also variance of mu hat of n, which is 1 upon n into variance of my h of xi. Okay, and now you know what is variance of my xi. Correct? Now you know the variance of my h of xi is going to be, it's integration h of xi square f of x d of x minus mu hat square. Okay, so by applying the your CLT theorem, one can say that the root of n mu hat of n minus mu, this is having the distribution with mean 0 and variance is going to be your under the function f h of x with the mean and with the variances, right? As you are saying n tending to infinity, because it will have the same distribution which is the normal with mean 0 and the variance is h of x, variance with this h of x. Are you getting this point? This is the one approach. This is the one approach. Other approach is that, now another approach is what? Another approach can be using another density function. Now see, I'm introducing the another density function. Let's say that is a q of x, as mu is equal to, this is your h of x usual function, this we have already, into your probability which is already there, into d of x will be there. Now I am dividing by q of x into q of x multiply. So how we can write this expression? So just look at this expression. This expression is exactly same as this expression. Can you observe? H of x p of x dx, h of x p of x ds. Okay, here I know I am not getting the sufficient information like we have seen for the normal distribution. It is giving the maybe many time it is giving me a single observation. There is no observation exists. So our ordinary method fails here. So we have to introduce some other sampling. We have to introduce some other method or approach where we should get the answers. Okay. So that's why the important sampling come in picture, and that's why we have introduced here q of x. Now, what is the q of x? Now, if you just look at this particular integration, this I can write mathematically, integration h of x p of x upon q of x. This will be as a one term into u of x d of x. Okay, and this I can write expected value of q h of x p of x upon q of x. Actually, ideally you should take everywhere small x here, because you are writing under the function f. Okay, under the integration. So whenever you take under integration, you must take always small x. Okay, but when you write under expectation, you should have always a capital X. So is it something like your expected value of x again here under the q probability, under the probability function is q? So this is again same as your usual method, you can say, and hence we propose that is a new estimate, which is mu star n, which is same as 1 upon n summation I is running from 1 to n h of yi p of yi upon p of yi. Are you getting this? What we did exactly here? Now the main question is here, how we define this q of x. So defining this q of x, and here this q is known as an importance distribution. Q is known as a importance distribution. So there has to be some condition on that, and we have already seen defining this p of x and this particular q of x must have the same support, must have the same support or q of x having the wider support as compared to p of x. So suppose my p of x is 0 to 1, so my q of x must be you may say 0 to -1 to 0, like -1 to 3, like so so it having the wider range as compared to p of x, or it having the same support. That's a one important thing you have to always introduce in this case, right? So here you may have where y1, y2, so on yn are IID with density function, with density, such a distribution q is called as importance distribution. Can you understand? Any query here? Go through from here. Just go through from here and let me know if you have any query here.
Yes, sir, done.
Done.
Done, sir. Done, sir.
So let us take one problem based on this important sampling. Let's take this example number 1. Suppose we say I have this h of x function is equal to 1 when x will be greater than or equal to 5, and equal to 0 when x will be less than 5. Okay, and my p of x is going to be, it's your standard normal, so it is 1 upon root 2 pi e raised to minus x square upon 2. Means you can either write f of x, doesn't matter here. So get the range here, x belongs to your real number. Okay, so the first task is that here we need to be compute, here we need to compute, to compute mu here, which is usual definition, expected value of p into under the h of x. That means I'm interested to compute the probability under p when x will be greater than or equal to 5. So this is my interest. This is my, this is my, this is my interest. Okay. So what I'm going to do, I'm going to just using the ordinary Monte Carlo technique, I will be just get the x1, x2, xn observations, which is IID from the normal 0, 1. Usual procedure, we have already seen this procedure last in the previous video, and compute mu hat using this formula 1 upon n summation of your i's running from 1 to n h of xi, correct? Which is same as 1 upon n summation i's running from 1 to n into probability of your xi greater than 5, or you can consider the indicator function. You can consider the indicator function. Okay, but what do you think about what do you think about this the estimated value which you have computed? What would be the accuracy of this particular estimate? Is this having the good accuracy, or whether this estimated value which you have obtained, it is the good estimator? So we need to check little bit their properties and all. Okay, so what would be the good, like what is the accuracy of this model? What is the accuracy of this mu hat in estimating mu? So one can use either there are so many methods here. One can use absolute error. Generally, you have used absolute error and relative error to check their uh, usual estimates are good or not. In Bayesian, you have already studied loss function, risk function. Right? That was a measure of estimate of the accuracy. One can use relative error. Okay, which is your simply mu hat upon mu hat minus mu upon mu. Okay, this is the another measure. So now we should know the distribution of that. So again, root n mu hat minus mu, this will be approximately by no central limit theorem, or we call of large number. One can say that this follows this in 0 and the variance mu 1 minus mu, right? And it is degenerate distribution. So root n mu hat n minus mu, this having the distribution with root of n 1 minus root of n into z, right? This z like properly here, right? Where z follows where z follows normal with 0 comma 1. Okay, so we'll just say up till here. Okay, but remember, when the mu is equal to 1, then this quantity becomes 0. That problem we can always, if the mu is very close to 1, that means we have the higher accuracy, because the variance is 0. No? Getting the point? So if the mu become near to 1, then we get the variance becomes 0. Okay, that means it is, we can say that it is the, it having the higher accuracy. Higher accuracy is achieved even the sample size is small, but mu nearby is to, it should be 1, but it can be close to 0.5 also. Depends upon that. So that's why the absolute error, instead of absolute error, one can go with always the relative error, because that should be that would maybe give the better result. That may give the better result, because here if you just consider, let us consider, like if you just consider, for example, mu hat, for example, let's say, let's say if mu is equal to 10 raised to minus 7, 10 raised to minus 6, for example. Okay, and let's say mu hat which you observed, which is 10 raised to minus 6. Okay, then what would be your mu hat minus mu? That means your absolute error, mu hat minus mu, which give us approximate answer is 0, right? Approximate answer is 0. Can you understand? Or you may consider, suppose, different value, for example, because here it will give you the answer definitely 0, right? Definitely it will give the answer is 0. But suppose if you just consider here 10 raised to, for example, some other value, or let's say this is 3, for example. Okay, so what would be this value? Anyone can calculate with the help of just calculate using calculator. So how it will give you? Is it approximate 0?
Minus 9.99 into 10 raised to minus 4.
10 raised to minus
4.
4. Okay, so means can we say it is approximate 0?
Yes.
Yeah. So if you just observe this absolute error will slightly having this problem with this absolute error, but just think of the relative measure, relative error here. Just think of relative error. What should be this? So mu hat minus mu upon mu. What would be it is? Just check. Camera answers.
999.
Exactly. So this is 2, this is 6. So this is 10 raised to 6. So this will give you the triple 9. Okay, so using this method I'm getting this difference is 0, where using this method I'm getting the sum answer. Okay, so these type of problems we have always uh, occurring while considering these estimates. Okay, so make sure that whenever you consider the example, you should always consider properly. Okay, so estimates are like not always